So it's 300 meters divided by 4.48 seconds. That looks like it should come out to be something like, yeah, I was going to say around 70. So 67 meters per second. And I would use x is equal to v0t plus 1/2 at squared. Did they say from rest?
Yes.
Yes. So then a is equal to 2x over t squared. That should look very familiar from the lab, yes? So then that's 600 divided by, like, I don't know, 16, if I were saying 20, or 620, 30? What is it? 29. So I'll say 30 meters per second squared. Bingo. To the instantaneous. So we know the average velocity to be, what was it, 67? 67 meters per second. So the question is, when is the instantaneous velocity 67 meters per second? Or when is v final 67 meters per second? Well, this is pretty straightforward because I know acceleration, don't I? Which is 30. So I just say Vf is equal to V0 plus AT. What was V0 again? Careful, V0?
0.
Right? And started from rest, so that's 0. So I get T. Did it ask when or where? When? Okay, cool. Where would be like where or how long, at what distance? That would be different. So T is equal to Vf over A. So I get 67 meters per second divided by 30 meters per second squared, and that's going to give me something like 2.2 seconds. So the rocket seconds. And at some point, I don't know, whatever, like some point here, right there, the velocity is 67 meters per second. We need to know the height at that point. Yeah. So what we know about the bolt already is that once it's in the air, its acceleration is negative 10 meters per second squared, right? We need to know the height that the bolt leaves at. Well, we know, what do we know? We know that the final velocity for this height, so if we say, okay, now I want to find this height, the final velocity is 67 meters per second. We know the initial velocity is 0, and we know the acceleration was, for that part, was what? 4, no, what was the acceleration? No, that's when the bolt leaves in the air. 30, there you go. 30 meters per second squared. This is when that, like the acceleration when the rocket was thrusting. Like, you know, as it was going up from 0 to the average velocity part. So then at this point, we can now say Vf squared is equal to V0 squared plus 2ax, or 2ah as the case may be. So x, which is equal to h, is going to be Vf squared, this is 0, Vf squared all over 2a. So 67 squared divided by 60. So that's going to be, so you say 0.160. Is that 6? 6 or 7? What do you get? Yeah, it should be around that. 74, 75, whatever. And now that we know this, if we know this is 75 meters, we're looking for, okay, we don't need this anymore. We're looking for the time of flight in the air. So then look at my variables. Right, VA, X, and T. So I use X equals V0T plus 1/2 AT squared. So X is going to be, what we're doing now is we're looking for when this thing falls back down to the ground. So our start time is right here. Start time is in the air, and then it falls back down to the ground. So we're at a height of 75. So it's negative 75, and then this is 67t, and then this is minus 5t squared. This is obviously the hardest thing we've faced so far. We have to realize the whole thing is 67 meters per second. And we know at some point right here, the instantaneous velocity is 67 meters per second. Please notice there's a difference between V bar and V. Okay? This must have taken some amount of height to get there. It also probably took some time. We knew that time was 2.2 seconds. right? We know the acceleration for this whole thing is 30 meters per second squared. The height is 300 meters. Okay, so what we did was we said, okay, I just need h. Because if I need h, or if I have h, then when we look at this equation, x equals v0t plus 1/2 at squared, we have h, we have v0, and we have the acceleration of the thing in the air. Because do you see that the acceleration of the rocket is 30 meters per second squared, but the acceleration of the bolt after it leaves the rocket is just gravity. Does that make sense? Yes? No? Second. The bolt goes xb in 1 second. Okay? And then we're looking for the difference, that delta x. So, for the rocket, for xr, we know the acceleration of the rocket is 30 meters per second squared. We know the initial velocity of the rocket. The bolt falling off starts this whole thing. So v0 is 67 meters per second. Is that the original v0? Absolutely not. Why does it work? Why is that the v0 now? Because we're concerned with from the moment the bolt falls off until a second later. So we're saying that this initial is that. And we say this is time of 1 second. And we want to know x. Can we come up with that using those numbers? Yeah, absolutely. Everything's there. 67 times 1 second plus 1/2 times 30 times 1 second squared. So that's going to be 67 plus 15, which gives you 82 meters. So let's talk about relation to the bolt. What is the acceleration of the bolt? -10, good, because of gravity. What is the initial velocity of the bolt? Right, because it just fell off the rocket, yes? And then we have t of, whoops, just kidding, t of 1 second. It's like the same stuff, just a different acceleration. So then I do the same equation. xb this time is going to be 67, again with the 1 second, but now it's plus 1/2 -10 times 1 squared. So basically I get 67 minus 5. And so I get 62 meters. So xr is 82 meters. xb is 62 meters. And therefore delta x is 20 meters. And bingo, that's it.